In this video, I'm going to quickly take you through how to generate an ECDSA public-private key pair, ECDSA using the Bitcoin Coblitz curve, and then I'm also going to quickly take you through deriving a Bitcoin address from the public key portion of that key pair, and then deriving a wallet import format key from the private key. So before we get into the code and whatnot, I just want to quickly discuss what ECDSA is. And we covered a little bit in this chapter, and the digital signatures Bitcoin primitives course goes into it in much more detail. But just to give you kind of an idea of what's happening here. So basically, this curve here is representing our space. So our space from 0 to n. And so all those points can be generated based on the geometry, the shape of this curve, and it gives it some unique properties. And one of the interesting things about these curves is it's difficult to actually, it's a difficult problem to actually figure out all of the n values for them. So there's specific curves that are used, and in Bitcoin it's SECP 256K1 Coblitz curve, a specific type of ECDSA curve that's used. But essentially what's happening here is you choose a generator point G on this curve, and then you use tangentials, you use tangential lines and scalar addition to find further points. And so you, like if you chose a point G here, you would draw a tangent line and you would find where it intersects with the line here, and then you would actually just do a mirror of that, and that would be adding 1. And then to add 2, you draw a line through there, and then you mirror it again, and it would be somewhere over here, and etc., etc. And so what's interesting about this is you never wind up hitting the same point twice. And also, as you do this, it's quite random in the way that these points are derived. So you do this enough times to an order of a certain amount, it becomes computationally infeasible to try and reverse from one of those points to find one of the other points. And so you create this public-private key pair between 2 points, because if you have your generator point and then you choose your private key as one of those points to a certain order, and then from your private key it has a corresponding public key, it's computationally infeasible to find the private key if you have access to that public key, because of this tangential scalar process, this addition, this point addition that's happening. And so one of the advantages for using ECDSA curves like this over traditional methods or other methods where you're using really big prime numbers is you don't need a number as big, because it's actually more difficult to try and reverse an ECDSA process than it is to try and reverse using a regular RSA process, or the process that RSA uses, or old-fashioned Diffie-Hellman and stuff like that, where you need a bit value now that's like between 2,000 and 4,000. Whereas with ECDSA, like Bitcoin uses a bit size of 256, it's the same as a SHA output. So it's significantly more efficient in that respect. And so what we're going to do here is we're going to choose, we have our generator point, and we have our curve, we have our n value. And remember, in computer science, the modulus operator, it's used to find the remainder of some kind of a division. So when you do a division between 2 numbers and you get a remainder number, that's the answer to the modulus. So in computer science, that's used a lot to restrict outputs to a certain size. And so if you want to keep things within like a 256-bit length, for example, what you would do is you would modulus whatever number you're using by 256. And then regardless of what number you're using, it's going to be restricted within that space of 0 to 256, because it's being modulus 256, so you're going to be using that remainder. Okay, so jumping into our terminal again, jumping into our tmux, I'm just going to go through a couple of examples. So first, what we're doing here is we're generating a public-private key pair using our Coblitz curve. So we got our generator point, we have our curve like we just talked about, our n value, and we're finding a pair of points within that space, so on that curve within that space. And then what we're going to do is we're going to take the public key of that key pair, and we're going to compress it first, and then we're going to turn it into a Bitcoin address. And then we're going to take the private key and we're going to turn that into a wallet import format key. And the two outputs are similar in the sense that they both use base 58 check to display them, but how you actually derive them is a little bit different. So the first one we're going to do is the address. But before we actually get the address, we need to generate a key pair, and that's what this line right here is doing. We're using the libsv libraries again, like we talked about in previous videos in this course. But yeah, so here we have the private key being derived from that Codlitz curve, and that's nicely abstracted in the libsv libraries for us. So we're calling this package, and then we're calling the function new private key from this BEC package, and then we're specifying that 256K1 Codlitz curve from that package as well. And so once we have our private key, as we talked about, we can use that point addition to derive a public key from that. And so that's, again, it's nicely abstracted away here, but that's what this step is doing here. So just to give you some output here, let's just run this really quickly. There we go. And so we can have a look at these outputs as we go through this. So this is our private key, and that's on that Codlitz curve. And then we're deriving a public key from that, but one step that's kind of just two steps in one here. We're deriving a public key from this private key, but we're also compressing it. And all that means is we don't actually need both points of the public key to have enough complexity in order for things to stay secure. So we can actually drop the y coordinate completely and use the x coordinate as well as one prepended byte that denotes whether or not the y coordinate is even or odd. And we can actually get the y coordinate using that, but we don't actually need it in order for this to be a secure way to do things. So we just drop the y coordinate entirely, and we use a compressed form of the x coordinate, or of the point, which is just the x coordinate plus that prepended byte denoting whether or not the y coordinate is even or odd. And so Bitcoin addresses are essentially the SHA-256 and then RIPE-MD 160 hashes. That's also referred to often as hash 160. That's the hash 160 of this compressed public key. And then what we actually do is once we have that double hash, we prepend it with 0 byte in this case, because we're just going to do this as an example mainnet address. And then what we do, we have our version here. So we have our version byte, and what we're doing right, like in this step, we're basically creating an empty byte array, and then we're prepending our version 0 for the mainnet, or 4D here for the testnet. And then once we have that, we then append the resulting double hash value to that version byte. And then from there, we can derive our address, and that's basically just the base 58 check encoding of all of those values. And you'll see the values here on the right hand side. So we have our X point, we have our Y point, and then we have our compressed key here, which is, this is in hexadecimal, this is actually in decimal, and this is also in decimal, and then this is in hexadecimal with that prepended byte. And so if we have a look and see here, we'll notice that this is a 3, and that's saying that our Y coordinate is odd. And you'll see it ends in a 9, so yeah, it is odd. And then just to further clarify this, I'll actually take you through it step by step using the hashing calculator available on the website, so you can try this for yourself too. And so I actually have this listed here twice because we're doing this the long way initially to derive this first address value, which is right here. So we're doing this step by step, and then it's actually already abstracted away. We can just call this function from this package here, this bscript package, and it actually has an address string function in it for us, so we don't need to do all these steps, but just to show you how this is actually working. So switching over to the hash calculator, let's just copy our compressed public key value here first, and then I'll pull this up. Okay, so we've copied our key value, our compressed key value. So the first thing we're going to do is make sure this is default ASCII, so make sure this is in hex, and then we need to get our hash 160 value from our compressed public key. So we can calculate that out, we'll copy that, and we can just put it in our address bar here for now, so it's there. And so from there, let's paste that in here, and then we need to add our version byte. We need to prepend our version byte, and this is a main net address, so it's a 0 byte, so we'll put our 0 byte in there. And then after that, we will get rid of that because we're not going to be doing any hashing, but this is still in hexadecimal, and now we want it in base 58 check. So we're going to do that, and then we're going to click calculate, and there it is. That is our Bitcoin address. And so we'll just copy that. And if we go back to our command line here, you'll notice that there's our address there. And so let's just paste the one that we just generated. And sure enough, they match. And so now we know how to generate our address. Let's have a look at generating our wallet import format key from our private key. And so we'll just jump out here, CD out of there, and we'll CD into the WIF example. And then we can jump into our Explorer here, into our WIF example. Okay, and so the WIF generation is pretty similar to the address generation. There are a few key differences though. I'm just going to run this really quickly so that we can have a look at the output as we go along here. But if we jump into the code now, so we're generating our private key like we did for the address. And then from there, we're actually serializing it and we're isolating one value from that generation, which is the D value, rather than in the public key was the X value. And then from there, we're actually creating the extended private key. It's a little bit out of order here, but this is the serialized version and then the extended private key. And with this extended private key, as you'll see here, so we're basically creating a blank byte array, and then we're appending it with 1 in hexadecimal. It's an EF or a 5 value for the testnet, and then we're appending our serialized key here after that. And then we're also appending a 1, and what this 1 is denoting is the corresponding public key that can be derived from this private key is in compressed form. So it's just that X with the prepended byte denoting whether or not the Y coordinate of the public key is even or odd. And so once we have our extended private key, then we can calculate our checksum. And so our checksum, this is a little bit of a different process from the address. And so what we're doing here is first, we're just going to get our checksum, which we need for our base 58 check. And that is a double SHA-256 hash or hash 256 of this extended private key. And then what we do is we take the first 4 bytes of that checksum and we append it to our extended private key. And then once we've done that, we have that checksum appended, and we can actually encode it all into base 58, and that gives us our wallet import format key. And so just like we did with the address, I'll show you an example of that using the hash calculator. So before I do that, I'll just copy the serialized version of our private key here. And then we'll pull our hash calculator back up. We'll just get rid of that value. We'll paste in our private key. We know that's in hexadecimal, and that's also in hexadecimal, our output. And so what we'll do here is, remember, we want to prepend our version byte, and so we're prepending that with a 1, and it would be a 5 if we were the EF, or a 5 if we were doing a testnet address. And then we also want to append our number 1 to denote that this is a compressed, the corresponding public key to this private key would be compressed. And then from there, we need to generate our hash 256. So let's go ahead and do that. We calculate that out, then we'll save the first 4 bytes. So 1, 2, 3, and 4. And we'll copy that, and we will append that to our extended private key. And once we've done that, we can just get rid of that hash 25. And our input is still in hex, but our output is now going to be in base 58. Remember, we're not going to do a base 58 check because we've already calculated that check out. And if we do a calculate hash, here we go. We now have our wallet import format key. So if we copy that, and then let's just go back to our command line here, we can paste that in, and sure enough, they match. And so hopefully this has demystified this a little bit, given you an idea of how Bitcoin addresses and Bitcoin WIFs are calculated. Basically, you're just using hashing again, and then you're using the base 58 encoding or base 58 check encoding in a couple of different ways, but that allows you to, again, in chapter 2 we covered how using those encodings allow you to transfer those addresses and those keys more reliably and more securely across a wider variety of communication channels that maybe only support text values. So like email would be an example, although you probably don't want to be sharing your WIF over email, but your public key for sure. But anyways, hopefully that clarified some stuff for you, and I'll see you in the next chapter.